Hello, hello, hello. This is Nicholas. Have you heard about the new broom sweeping the nation? Neither have I. Anyways, there were a couple properties in the last video that I talked about with limits that I just forgot to mention that, and so I'm going to mention them here. I gave you these two properties about limits. Well, they're really three. There was some other ones I just forgot to mention. If you have the limit as x approaches a of f of x times g of x, then you can separate it out as the limit as x approaches a of f of x times the limit as x approaches a of g of x. So the limit of a product is the product of the limits. And the limit of a sum is the sum of the limits. And the limit of a difference is the difference of the limits. And also, if this were division, then there would be division there as well. So the limit of a quotient is the quotient of the limits. If you have a power, then let's say, for example, you have the limit as x approaches a. You don't use this rule too much, but if you have the limit as x approaches a of f of x to the n, you can take that and write it as the limit as x approaches a of f of x, and you can take that limit and raise that whole answer to the nth power. Likewise, if you had the nth root, you could, if you had the nth root, you had the nth root of a function. The nth root is really 1 over n as an exponent, so you can make it a 1 over n there as well. Okay, so we're going to be dealing with some limits at infinity. And I'm going to be hopefully alleviating some confusion from your Algebra 2 class, from some things that you have just kind of taken for granted in Algebra 2. So now, let's say, for example, we have the limit as x approaches infinity of 2x to the fourth minus x squared minus 8x. How would you go about doing that? If you directly substituted, right, you'd get infinity minus infinity minus infinity. That's really indeterminate. So we need to do some work. Wouldn't it be nice if instead, say, this x squared were a 1 over x squared? Because if I were to take the limit as x approaches infinity of 1 over x squared, that would obviously be 0. The denominator becomes increasingly large and the numerator stays fixed. So you go to 0. For example, 1 over a Brazilian goes to 0. How many is in a Brazilian? Anyways, so I could make this the limit as x approaches infinity of, and what I could do now is I could actually pull out the biggest factor. This is generally the idea with limits at infinity. Pull out the biggest factor, and I can make it x to the fourth. Let me put brackets here. X to the fourth times 2 minus 1 over x squared minus 8 over x cubed. And now what we can do... Oh, by the way, this might be unusual for you to do, right? Normally, you're used to factoring out the lowest common factor, which in this case would be an x, but it is usually better with limits at infinity to factor out the biggest factor, because then all the other factors smaller than it will be on the denominator, and so then those will go to 0. Now, this is the limit of a product, so we can make this the limit as x approaches infinity of x to the fourth times the limit as x approaches infinity of 2 minus 1 over x squared minus 8 over x cubed. Okay, this limit here, as you plug in infinity, you don't plug in infinity, as x gets bigger and bigger, this 1 over x squared goes to 0, and the 8 over x cubed goes to 0. So you just get 2 for that limit. But this limit here is problematic, because as x gets bigger and bigger, x to the 4th really gets bigger and bigger by a factor of 4x's. So this limit here is infinity, or it does not exist. So since this limit doesn't exist, the whole product doesn't exist, and so the answer would either be infinity, that's the best answer, or I guess technically you could write dne does not exist, because the limit doesn't have a finite value, but the infinity does tell you more, so that's what I would write. So yeah, you see something like this, you can pull out the biggest factor, and that will get you your answer. Now, that's an uncommon type of limit. Usually you'll see them as quotients. So let's do an example. Let's do the limit as x approaches infinity of 2x to the 4th minus x squared plus 8x over negative 5x to the 4th plus 7. Now, I know from just looking at this limit that the answer is going to be negative 2/5. How did I get negative 2/5? Oh, well, because I looked at the answer beforehand. No, I'm just kidding. That would be cheating, right? Okay, well, let me show you the systematic way to do this first, and then let me show you the quick way after, because knowing the systematic way is still important, I think. What I can do is I can essentially multiply by the, I'll just write it. I'm going to multiply by 1 over x to the 4th over 1 over x to the 4th. Why? Because then you get the limit as x approaches infinity of just 2 minus 1 over x squared plus 8 over x cubed over negative 5 plus 7 over x to the 4th. So why did I choose to multiply by the 1 over x to the 4th on the numerator and on the denominator? Because that's the biggest factor of x that appears, right? See, I want my x's to be all on the denominator, because then the whole term will go to 0 as x gets bigger and bigger. I don't want them to be on the numerator. So I multiplied by the reciprocal of the biggest factor so that I could make that happen. That's what I did. Now, when I plug in infinity, you can see the benefits of this, because when I plug in infinity, the 2, well, that's just 2. 2 is always 2. This goes to 0. That goes to 0. That goes to 0. And so all of those go away. And you just get the 2 over negative 5. And so the answer actually is a negative 2/5. Now, let me show you the cool way to go about evaluating these limits. This is how the cool kids evaluate limits at infinity. You look at the limit and you say, well, as x gets bigger and bigger and bigger, this x to the 4th, this 2x to the 4th, and this negative 5x to the 4th, those are going to be, this is a loose definition, but those are going to be the dominating terms on the numerator and the denominator, respectively. Why do we call them the dominating terms? Because they are going to outpace this. For example, the 2x to the 4th is going to outpace the x squared and the 8x. As x gets bigger and bigger and bigger, this 2x to the 4th here is going to grow much, much faster than this x squared or this 8x. And that should be clear, right? It's got a higher exponent and it's got more factors. For example, 1,000,000 to the 4th is much greater than 1,000,000 squared, which is much greater than 8 times 1,000,000. And so as these x gets bigger and bigger and bigger, these terms here, this x squared and the 8x, they just go to 0. They're insignificant relative to this 2x to the 4th, this dominating term here. And likewise, the 7 is a constant, right? So it's not changing at all as x gets bigger and bigger. But this negative 5x to the 4th is going to be like negative 5 Brazilian million trillion. I'm counting like Joe Biden. But it's going to get massive. And so this 7 is going to get infinitely small relative to how quickly that negative 5x to the fourth grows. You can just get rid of it. You just get rid of the 7. It goes to 0. It's insignificant relative to the dominating terms. And once you get rid of those dominating terms, you just get once you get rid of everything but the dominating terms, you get the limit as x approaches infinity of 2x to the fourth over negative 5x to the fourth. Cancel out the x to the fourths, and you get negative 2/5. So what you really can say in your head is, well, look at the degrees of each term, the exponent on each term, and you say, well, just take the ratio of the coefficients of the highest degree term, right? You have the highest on the numerator. The highest degree term is a 2 or is a 4. It's an exponent of 4. Let me write the numerator again. I've done so many circles. Plus 8x over negative 5x to the fourth plus 7. The biggest degree term on the numerator is a 4. The biggest degree term on the denominator is a 4. You can take the ratio of those leading coefficients, and that will give you a negative 2/5. And again, it's because these two terms here, it's because those two terms outpace dramatically the other terms here and here as x gets bigger and bigger. They become insignificant. I hope that the fact of them becoming insignificant is clear to you. And this is why in your Algebra 2 class, your Algebra 2 teacher said to you, when we're doing horizontal asymptotes, for example, and horizontal asymptotes with the rational functions, and your Algebra 2 teacher said to you, well, if you've got a function f of x, and it's some function p of x over some function q of x, and if p and q are the same degree, in other words, they have the same highest exponent, in this case, degree 4, just take the ratio of the leading coefficients, and that's what the function is going to approach. Now we know for sure that the function approaches that value, and your Algebra 2 teacher was right because of this calculus here. The calculus tells you that that's why the horizontal asymptote is what it is. As another example, let's say I had the limit as x approaches infinity of x cubed minus 2x squared minus 3x minus 4 over x squared minus 2x minus 3. What would this limit be? Just from looking at it, I know that this limit is going to be infinity or it won't exist. Why? Because this x cubed is the dominating term here in the numerator. It's going to outpace this term, and this term as x gets bigger and bigger and bigger because it's got more factors of x in it. And so these become insignificant as x gets bigger and bigger and bigger. And so you can effectively cancel them out since x is increasing without bounds. And likewise, this x squared is the dominating term on the denominator. And so this 2x and this 3 are going to become insignificant relative to the x squared. And you can, again, effectively cancel them out because the limit is increasing without bounds. So now we get the limit as x approaches infinity of just an x cubed over an x squared, which is just the limit as x approaches infinity of x, which is obviously infinity, right? X gets bigger and bigger, the whole limit just gets bigger and bigger. And this is why in Algebra 2, they said to you, if the degree of p of x is, say, 3, which is greater than the degree of q of x, which is, say, 2, then there is no horizontal asymptote. The function doesn't approach anything as x increases without bounds or decreases without bounds if this were as x approaches negative infinity. So these are where these Algebra 2 rules are coming from. They're not just hocus pocus. One more example. Let's flip it. Let's say we have the limit as x approaches infinity of let's flip it. Let's make it x squared minus 2x minus 3 over x cubed minus 2x squared minus 3x minus 4. All I've done is flip the fraction. Now I can tell right away that that limit's going to be 0. Why? Again, this x squared is the dominating term. We can get rid of the 2x and the 3. This x cubed is the dominating term. We can get rid of the 2x squared, the 3x, and the 4. And so we're left with the limit as x approaches infinity of x squared over x cubed, which is the limit as x approaches infinity of 1 over x, which is just 0. So the whole limit's 0. And this is why in Algebra 2, they said if the degree of p of x, which is in this case 2, is less than the degree of q of x, which is, say, 3, then the horizontal asymptote is just at the x-axis. It's just at y equals 0. I hope you see now that your Algebra 2 teachers, while they probably didn't know that this was the reason why, because most Algebra 2 teachers aren't that great of Algebra 2 teachers, this is where those rules are coming from. Okay. Maybe as one more example, I do want to do just one at negative infinity. Limit as x approaches negative infinity of, I don't know, x to the 4th minus 2x squared minus 7 over x squared plus 3. So now if we were to get rid of everything but the dominating terms, we would just have we could get rid of this 2x squared and the 7, and we could get rid of the 3, and we would just have the limit as x approaches negative infinity of x squared. And now as you plug in negative infinity, right, x squared is a parabola. It goes up like this and up like that. So the whole limit just becomes infinity because you get bigger and bigger numbers as you go to the left of this parabola.